Today we're going to talk about the molar volume of a gas. We've talked about molar mass before. Molar mass, remember, is the mass of 1 mole of a substance. We get that value from the periodic table, from the atomic masses. And that value in grams is how much 1 mole weighs. Now, when we talk about a gas, we can also come up with another um, constant, another conversion factor, and that deals with how much space 1 mole of a particular gas occupies when it's under something called standard conditions. STP is the term that we use when we're dealing with gases. Because gases are so variable in their characteristics depending on the temperature and pressure, we have this set of standard conditions, again called STP, which stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. It's the amount of pressure, air pressure, that exists at sea level, and we call that 1 atmosphere. So under these conditions, these standard conditions, STP, 1 mole of any gas will have the same volume. Because remember, a gas is so spread apart, there's so much free space in there that no matter what the size of the gas particles are, they're still going to occupy the same overall volume. It's like taking in at someplace the area of Dallas-Fort Worth and putting 10 bicycles or 10 18-wheelers in that space. It really doesn't matter how big the bicycle is, how big the 18-wheeler is, because there's just so much empty space that the size of the actual particles doesn't matter. So the overall volume of a gas is a standard value at STP for any gas, and that standard value is 22.4 liters per mole. We can take that value and turn it into a conversion factor. So if we say that there are 22.4 liters of a particular gas in 1 mole of that gas, remember we can also say that there's 1 mole of the gas for every 22.4 liters. So those are conversion factors that we can use anytime the volume of a particular gas, if that we are questioned about the volume of gas at STP. So let's see how we use that new conversion factor. So the first question, what is the volume of 5.0 moles of CO2 at STP? As soon as we see this STP and we see we're working with a gas, we know that we can use the conversion factor 22.4 liters per mole. So what do I expect you to do on these problems? I expect you to underline the piece of information that's given. I expect you to circle what it's asking for. As soon as it asks for volume, when we're dealing with gases in this particular area of chemistry, we're going to know that it's talking about liters. Now, I'm going to go ahead and put that in green because you don't have to have that, but I do expect you to still attack the problem by underlining what you're given and circling what you're trying to find. So we start out with our value again, that's underlined, 5.0 moles of CO2. Now, a lot of y'all are missing points because you're not putting the substance with the unit. I'm never going to give up on that. You're going to continue to miss points if you don't keep writing that substance with the unit. Now, we may not know much about the next conversion factor, but we do know that moles of CO2 has to go on bottom so that it will cancel. So moles of CO2 are canceling here. Remember, with our conversion factors, the number 1 always goes with mole. So we know that 1 goes with mole for CO2. And we have a direct conversion factor to go from moles to liters, and that's our new molar volume. 22.4 liters of CO2 is what 1 mole of CO2 occupies. We get ready to circle that. We see that that is what it's asking us for. It's asking us to find volume. When we multiply those two together, since they're side by side, we come up with 112. Just as another reminder, we need to get that to a USS answer. It's a number greater than, and I'm going to put this in green because you don't have to put the interim value, but it's a good idea to. So 112, we want to move that decimal point to here. It's understood to be here, but we want to move it. It's a number greater than 1, so it's going to be times 10 to a positive. Looks like we moved it 2 places, positive 2, 1.12. We look at our value, and our values here have 2 sig figs for this value, 3 sig figs for this value. So it looks like we're going to need 2 sig figs. So we draw our line here, and we end up with a value of 1.1 times 10 to the second liters of CO2. Okay, so I'm not going to require you to do brackets on these problems because there can be more than one conversion factor. So I never have you do brackets whenever we're working with those kind of problems. But again, there are still some things that you have to have. You still have to have this underlined. You still have to have what it's looking for circled. It's at STP. Again, that just opens up the fact that we can use that 22.4 liters per mole. We start with our value 100.0, the value that's underlined, liters of N2O3. That substance has to be there. You're going to continue to lose points if you don't put it there. So we put that in parentheses. And we don't know much, but we do know that liters of N2O3 has to go on the bottom, the next part, in order for it to cancel. Some of y'all aren't showing the canceling of your units, so you're getting values that are flipped in the conversion factor, and you're getting the wrong answer. So pay attention to your units. Now look back up at our molar volume. We need the one with liters on the bottom. The 22.4 goes with liters. And the 1, remember, goes with mole in the conversion factor, 1 mole of N2O3. So we've got that conversion factor written. We've canceled our units. We get ready to circle moles of N2O3, and we realize that that does not match grams that we circled in the problem. So we know we're not done yet. So we know we need moles of N2O3 on the bottom. And remember, in a conversion factor, the number 1 always goes with moles of N2O3. Getting problems with people knowing what to put here for their conversion factor. Remember, we've only got, now that we added molar mass, 3 conversion factors that we can use. We can use molar mass. We've got our molar volume we just talked about today. And we've got Avogadro's number. If we want to find grams, we're going to be looking at molar mass. If we want to find some kind of particle, whether it's atoms, molecules, or formula units, then we're going to use Avogadro's number. Now look at what we're trying to find here. We're trying to find grams. So if we're trying to find grams, we're going to need molar mass. Where do we get that value? Remember, we called that table grams as a little mnemonic device to help us remember that we find that value from the periodic table. So we need to look up and add up into O3. And if you do that, nitrogen is 14.01, but there are 2 of them. So adding those together, I get 28.02. And we've got 3 oxygens. Our 3 oxygens at 16 each gives us 48. And when we add those 2 together, we end up with 76.02 grams per mole. So there's our molar mass right here. That's what we're going to use in this value. Now, a lot of people are putting the 76.02 grams per mole on top. But remember, when we split that into a conversion factor, the mole goes on bottom. The only thing that goes on top is the grams. Now, I didn't leave myself enough room to write the N2O3, and that's important. I require it, so I'm going to erase that parentheses and spread it out a little bit so I can fit that in there. So now moles of N2O3 cancel. I'm left with grams of N2O3, and that's what I want in my problem. So when I put this in my calculator, I put in 100 divided by 22.4 times 76.02 since it's on top, and I end up with 339.375. Now that is a number greater than 1, so we know that we're going to have to use a positive exponent. I need the decimal to be here, and it looks like we moved it 2 places. So it looks like we're going to have times 10 to the positive 2. So 3.39375 times 10 to the second. Now if we look at the number of sig figs we've got, we have 4 sig figs for our given value. We have 3 sig figs for our molar volume and 4 sig figs for our molar mass. Looks like we're going to go with 3 sig figs. So we need to draw our line here. That next digit says I don't need to round up. I just leave it where it is, and I get 3.39 times 10 to the second grams of N2O3. So that's just adding in a new conversion factor. We now have molar mass, Avogadro's number, and molar volume. So I'm going to just write that one up. Remember, that's what you get when you're looking for volume or liters. So those are the only 3 conversion factors we're allowed to use on this worksheet that we're dealing with. Now, as far as the density of gases, we know that there is a equation for density, and that density is, if you remember this from earlier in the year, density is mass over volume. Well, the beautiful thing about gases is if we are at STP, now this is only true at STP, the density of a gas is going to be equal to its molar mass over its molar volume. That's going to give us our density. So no matter what the gas is, if we know molar mass and we do know molar volume at STP, it's a standard, it's a constant, 22.4 liters per mole, then we can find the density. So if I want to know the density of carbon monoxide at STP, I know that the density of carbon monoxide is equal to its molar mass divided by its molar volume. So if I look up the molar mass of carbon monoxide, I've got 12.01 for carbon, 16 for oxygen, and when I add them together, I get 28.01 grams per mole. Molar volume is a constant at STP, so for every gas we do, for every problem we do, this bottom value is always going to be 22.4 liters per mole. So when I look at my units, it looks like moles are going to cancel, and what I'm going to be left with is grams per liter, which is the common unit for the density of a gas. Remember, if we're dealing with a liquid or a solid, which are much more compressed, we deal with grams per milliliter or grams per cubic centimeter. But for a gas, we deal with grams per liter. So since we've got 28.01 over 22.4, we're going to divide, and we get that the density of carbon monoxide is going to be 1.25, 3 sig figs, times 10 to the 0, 1.25 times 10 to the 0 grams per liter for that density. In this case, since we've put the substance over here with density, we don't have to include it at the end of our problem with the unit.